Rising from the vast, enigmatic depths of our oceans stands an engineering marvel. Each rig is a self-contained city of steel, meticulously designed with a multitude of components. Fixed platforms are a cornerstone of offshore energy, designed for long-term operations in shallower waters. The intricate lattice structure, known as the jacket, provides immense strength and optimal load distribution.
Above the water, the platform deck houses vital equipment, from drilling units to production facilities, meticulously arranged for maximum efficiency.
This design allows them to withstand the harshest marine conditions, a permanent fixture against the vast, dynamic ocean.
These piles are meticulously driven into the seabed, creating an unyielding foundation.
Fixed platforms, with their permanent, robust foundations, are therefore perfectly suited for long-term operation. As we move into deeper waters, fixed platforms become impractical. Here, semi-submersibles These tanks are carefully filled or emptied with seawater, allowing the rig to be ballasted to the desired depth. This intricate system of interconnected buoyancy chambers, reinforced with strong structural elements, these crucial components are universally known as the ballast tanks, the main pontoons, and the vertical columns that connect to the platform deck. Despite surface waves, semi-submersibles maintain remarkable stability, thanks to their design that minimizes
The stability of a semi-submersible is geometrically defined by its stability triangle, an engineering principle ensuring.
Below the pontoons, powerful thrusters provide dynamic positioning, counteracting currents and winds. Through precise control of ballast water, these rigs can adjust their draft, enabling them to safely operate.
A defining feature is the moon pool, an opening through the hull that allows drilling equipment to be lowered directly into the ocean beneath the ship.
Directly above the moon pool, a complex array of drilling equipment, including the derrick and pipe handling systems.
Dynamic positioning systems utilize an array of powerful thrusters strategically placed around the hull. This advanced naval architecture ensures optimal stability and remarkable mobility, enabling drill ships. At the heart of every drill ship is the moon pool, a central opening in the hull that provides a protected conduit for drilling. This precise positioning is maintained through advanced dynamic positioning systems, utilizing.
While dynamic positioning offers immense flexibility, many floating rigs rely on robust mooring systems to maintain their precise location.
Traditional mooring systems typically employ multiple heavy anchor lines, securely extending from the rig to anchor points on the seabed. Each mooring line is a critical component, transmitting the rig's stability to the ocean floor, resisting the constant forces of currents and waves. This radial spread creates a highly stable platform, with each line's tension dynamically adjusted to counteract. Utilizing advanced CGI, we analyze the complex internal mechanisms and switches. This hyper-realistic visualization reveals the intricate engineering of the offshore platform, detailing the deep ocean environment provides unique challenges. Here we see the dynamic positioning system, and we zoom out. The intricate network of mooring lines and the dynamic positioning system ensure precise stability against the strongest currents. While mooring lines offer stability in shallower waters, deep water rigs require a more sophisticated solution. Central to these systems are powerful azimuth thrusters. Unlike fixed propellers, these units can rotate.
To achieve this precision, DP systems rely on an array of sensors. GPS provides.
This sensor data is fed into a central computer, which constantly calculates the rig's.
These commands activate powerful azimuth thrusters, which are capable of rotating 360 degrees.
An azimuth thruster's internal mechanics are engineered for efficiency, with powerful electric motors rotating large
By continuously monitoring external forces and making minute adjustments, the dynamic positioning system ensures.
Central to the drilling operation is the derrick, a towering structure designed to support the immense weight and forces.
This formidable structure is engineered for maximum strength, designed to withstand immense loads and the This intricate threading process creates a strong, high-pressure seal, critical for maintaining wellbore integrity. Once a section is added, the top drive rotates the entire drill string, grinding the drill bit into the formation. This continuously rotating drill string can extend for thousands of meters, a precise conduit through both the deep ocean. The integrity of each threaded joint is paramount. These connections are engineered to withstand immense torsional and
Journey into the Earth's crust begins with the drill bit, a marvel of engineering designed to precisely cut through formidable rock formations.
With immense force and precision, the drill bit carves through diverse rock strata, carefully dislodging and breaking down the earth layer by layer. Critical to the drilling process is the constant circulation of drilling mud. This specialized fluid cools the bit.
The camera follows the drill bit as it continues its relentless descent, traversing through hundreds of meters of diverse geological.
Crucial to this process is the drilling mud, which lubricates the bit, cools it, and most importantly, carries these rock cuttings up to the surface. Modern drilling is not always a straight shot. Through sophisticated directional drilling techniques, with the wellbore meticulously carved through diverse strata, it forms a perfectly smooth conduit. This completed.
The next critical phase begins with casing, where robust steel pipes are lowered into the wellbore, securing its integrity from top to bottom.
These casing strings form a protective barrier, preventing formation fluids from entering the wellbore and maintaining its structural integrity.
Once the casing is in place, cement slurry is pumped down, then pushed back up the annulus, filling the space between the casing and the rock formation.
This cement then hardens, forming a robust, impermeable seal that permanently bonds the casing to the. This multi-layered casing and cementing process is fundamental to creating a secure and environmentally sound well. The structural integrity of the wellbore is critical. Here the X-ray view highlights the strong bond between. This hyper-realistic 3D visualization details the complex subsea architecture.
Orbital view tracks the subsea manifold, showcasing the intricate network of pipes and valves facilitating the deep ocean energy transfer.
we track closer, the internal mechanisms of the three-phase separator become clear, efficiently isolating the oil, gas, and water. The processed hydrocarbons are then transferred via the riser system into the deep storage reservoirs below. This complete production system ensures efficient extraction, guiding the flow from the subsea wellhead directly to the surface. Offshore oil and gas rigs are not merely structures. They are monuments to human ingenuity and our relentless pursuit of energy. These marvels of engineering provide a vital energy supply, driving economies and supporting modern life across the globe.
From exploration to extraction, every component works in precise harmony, a testament to decades of technological innovation.
As the world continues to evolve, offshore energy will remain a critical pillar of our future, powering progress and possibility. This hyper-realistic visualization reveals the intricate engineering of the offshore oil rig,